All right, welcome back to Computer Science 50. This is the start of week 7. So we have some exciting stuff in store. This is officially the last week in lectures where we focus on C, although problem set 5 and ultimately 6 will continue to focus on C. Next Monday, though, do we dive into the world of web programming and talk a little bit about how networks work, how the internet works, what HTML, CSS, PHP, SQL, and a whole bunch of other things are. So we'll gradually transition to that starting quite soon. Before we begin today, thought we'd take this one last possible day to touch on something topical. 2 years ago, PC Magazine wrote this article, The 21 Biggest Technology Mistakes of 2006. Number 3 that year was hacking the vote. Are electronic voting machines insecure? In May, security researchers discovered a previously unknown backdoor in Diebold's AccuVote TS touchscreen voting system that could allow an attacker to manipulate votes, cause malfunctions, or create a voting virus that spreads from machine to machine, all in under a minute and with little fear of detection. So fortunately, 2 years have passed since that huge mistake on the world's part, and yet it's not hard to find such videos as these. Let me introduce you to touchscreens as they are today.
We're totally transparent here. We welcome anyone who would like to see how the machines operate, how the machines function. If the poll worker got to a machine and it was out of calibration, this is what would happen. I'm going to touch Barack Obama there, but notice it jumped clear down to Chuck Baldwin because the machine is out of calibration. Now it sent me to a screen to vote a write-in ballot. When I hit Barack Obama, the machine's out of calibration. It did not jump up to the Republican candidate. It did not vote a straight Republican ticket. It didn't do that. It jumped down to Chuck Baldwin. So, you know, the allegation that was made was they went to hit the Democrat and it jumped up to a Republican every time. Straight Democrat did go to John McCain this time. Straight Republican. I don't know if I can get it again. It slid over and did that. So then what do? You go back in and you try to recalibrate the machine. This machine is now calibrated. This is the same machine that was jumping all over the place just a few minutes ago. Let's see. Now it is functioning just as it should function. Up. If I go straight Republican. Oh, that's out of calibration. Notice Ralph Nader came up. If that happens, again, the machine lets you know. There are actually going to be techs trained by the ES&S. They can be dispatched there immediately. Look at the problem. You should never leave the voting booth without voting for who you should wanted to vote for.
So, it's not so much funny as it is kind of scary. I thought we'd use this as an opportunity to demonstrate a little e-voting program I wrote. Doesn't cost millions of dollars, but I'm pretty sure it's correct. I whipped this up early this morning kind of to demonstrate that these problems that these e-voting machines have and this bad rep that e-voting machines is really the result, I would dare say, of incompetence more than anything fundamentally technological. Harry Lewis teaches this course at the college called BITS. It is part of the core curriculum in QRR. And one of his visions for that course and courses like it, including perhaps our own, is to equip you guys not only to learn how to program and know a little something about a computer science, but ultimately if you end up in some position of business importance or political importance, some position of power in the future, that frankly you won't approach these kinds of roles without a modicum of understanding of how technology works. Clearly people have bought into machines like these and have spent millions of taxpayers' money on machines like these, and it seems to be this sort of accepted reality that these things just aren't perfect. And certainly voting has never been perfect ever since voting in this country began. But I argue that just with a little program like this, eVote, All right, so I implemented this in C, maybe like 30 lines of C, and I made a few what I would claim to be intelligent decisions. So first of all, I didn't choose 1 for Barack and 2 for John McCain. I'd instead tried to introduce a bit of intelligence whereby the user has to touch 1 over here for one user and 9 over here for another, instead of clustering these things, for instance, close on the screen. I went ahead and hit 1 here. Thank you for voting for Obama. It goes ahead and records that, presumably. Next person walks up. 9. Whoops. Damn it. Thank you for voting McCain. That was user error, not computer program error. Let's vote for McCain again. And how about another for Obama? Another for Obama, and now I'm going to hit a secret command called 0, which actually quits this thing. And it seems that Obama has, in fact, won. Now, one of the touted features, or lack thereof, a lot of these e-voting systems is the lack of a paper trail or actual recording. Well, using a little function that you all know called fopen and fprintf, well, it's not all that hard to maintain a log of everything that happened in a computer system. So here I simply chose a proprietary file format of my own where it says candidate's name, comma, and then a timestamp. This is a Unix timestamp, number of seconds since January 1, 1970, sort of the convention the world adopted. And that's it. If I need to go verify that it was in fact Obama that won, I just have to look at this text file. Suppose that the text file is really long. Well, there exist programs in this world to facilitate this. I can, for instance, use a command called cat. And I can which means concatenate. In this case, I'm concatenating one file with itself, which doesn't really have any meaning. But then I can pipe it recall. Oh, that's user error. I can pipe it recall into another command, as you did a couple problem sets ago, using something like grep. Grep is like a find, a control F type utility. And I can search, for instance, for Obama. That's only going to show me the rows in that file that say Obama. And if I don't even want to sit there, counting chads as happened 4 years ago, I can even then pipe it to a program called word count, give it a -L line switch, and voila, Obama's number of votes was 3. And so one of the lessons we honestly hope you take from this course in exchange for having sacrificed many, many, many hours of your life is, frankly, you won't exit this course an idiot when it comes to technology, because it is not hard to solve some of these problems. And I would dare say if people in positions of power, perhaps our friend Ted Stevens among them, perhaps this country would start making more intelligent technological decisions. So enough of my soapbox. Feel free to make use of that e-voting program if you would like. A couple of announcements today. One new handout including slides and lecture code. No walkthrough today. It already happened last week, so the video is in fact online. Cato led that walkthrough last Monday. And now a word on grades. Very dramatic game show style here. So unfortunately, there's nothing really fun about this. So quiz 0 was graded that same night, and some statistics were circulated. As we said there, that if you were in somewhere in the 40 range, you're doing pretty well. And I really wouldn't worry about how you're doing in the course. And if you do even better on quiz 1, wonderful. If you're in the 50s, fantastic. If you're in the 30s or lower, well, then it's time, I think, to care a bit more. Reach out to me, Jansu, your teaching fellow, attend office more. Really just sort of take ownership, if you care, to sort of raise yourself back up into, say, the range of the 40s and 50s. But with respect to problem sets, I wanted to address this, because we've gotten a few emails inquiring as to how problem sets are graded. As we say on each of the PDFs, there's 3 primary axes along which we grade these problem sets, and those are correctness, design, and style. And very intentionally do we whittle down what I know are for you 10, 15-hour problem sets into really just a very small number, very coarse buckets. And this is intentional because at the end of the day, we care more about looking for trending on an individual student basis, starting off at 3, working your way up to 4s and 5s, than we do about figuring out where the line is between a student who's going to get a 84% and an 85%. There's so much variability in the type of work submitted in a course like this, and there's even variability as much as we try to standardize it across sections. So inevitably, every semester, some TFs grade easier and some TFs grade harder, even though they're all executing the same grading guidelines that I myself have put forth. And so when it comes time, when students ask the TFs questions like, well, what letter grade am I going to get? Frankly, we have no predetermined distribution. We don't grade on some predetermined curve where this percent's going to get A's, this percent B's, this percent C's. I will say historically that the course, in exchange for your giving up so much of your lives, tends to be rather generous when it comes to rewarding said behavior at the end of the semester. And as I said early on, this is, I think, historically the type of course where if you do the work, and you do it well, you do well grade-wise in the course. It's not so much hard, a course like this, as it is for many students, simply time-consuming. And we do recognize that at course's end. We do tend to weight at the beginning of the course this metric known as correctness more heavily than design and style, since correctness is sort of more obvious. How you make a program consistent with the spec, you just compare your output versus what the problem set wanted. But design and style is really only something that you learn by way of practice, by way of example, and you only get more practice and more examples as the semester progresses. But the TFs by me have been very explicitly instructed in this first half of the semester to award very stingily grades like 5s and even sometimes 4s. I mean, though we don't disclose exactly how points here and points there are allocated publicly, internally, I have explicitly instructed the TFs that most students, for instance, for problem set 1, should get about a 3 when it comes to correctness, because, or rather for design, for instance, or for style, because invariably there is room for improvement. And so as the course progresses, internally, do we encourage the TFs to not only look for trending upward, but also to sort of accept the fact that students are presumably getting better and catching more things on their own and not looking so much to us. So this is to say, if you're starting the semester's problem sets getting a bunch of 3s, as we say on the website, that's good, and that's consistent with what directives I've provided to the teaching fellows. If you're ending the semester with 4s and 5s, all of the better. I fundamentally don't care all that much about grades, and I say this with a bit of retroactive hypocrisy, since when I was sort of sitting in Sanders looking this way, I very much more so did. I was much more uptight and anal as an undergrad, certainly, than I am now as a teacher. But from the course's perspective, these are more of a pedagogical tool than they are anything. So frankly, if you're a little bit stressed by the fact that you got a 41 on the quiz, or you only got a 3 on the problem set, frankly, all the better. That is exactly the purpose of them, to sort of drive you to improve over time and to see what, in fact, you could do better the next time around. But if you have any individual concerns, do approach me, do approach your teaching fellow, but do know now that grades are also normalized at the end of the semester across sections. So this also recurring theme of roommate and his roommate, who both are taking 50 but have different TFs, and they're comparing their problem sets after they've been graded and asking, well, wait a minute, why did your TF deduct more for this? Well, we account for that at course's end, because it happens invariably when you have such design-oriented and such problems that are by nature conducive to an infinite number of solutions in theory. So with that said, let us forge ahead, but do reach out to me or the TFs if you have additional questions or concerns. Here's a fun little tool. So we have focused on sort of helping you help yourself find bugs in your code, but thankfully there do exist tools. GDB is one of them, and moving forward with problem set 5 and 6, Valgrind is another one. The unfortunate aspect of Valgrind is that they made very little effort to make its output user-friendly. So you kind of have to read between the lines, but when you know what to look for, it's a wonderfully useful tool when it comes particularly to finding memory-related bugs. So let me show you this particular program, memory.c, which is among your printouts for today, and it's terribly small. It only has a main routine and a function called f, and there are 2 problems in it, one of which is unfortunately still on the screen, the other of which is also in your printout. But just looking, if you would, at the function called f, there are at least 2 bugs in that function. What are they? Stimulate yourself by not looking at the comments in the code. What's a bug in f, or in this overall program? Yeah? Excellent. So you're malloccing some memory, but you're never freeing it, which means your program runs the risk of some kind of memory leak. And in general, memory leaks are bad. They slow the machine down. They suck up memory even though you don't need it. And so in this case, it's sort of a glaring bug. Is there another one? Yeah.
X10 is outside bounds.
Yeah, so this is that indexing outside of the boundaries of your array. So if I'm mallocking 10 times size of int, that's just like saying give me space for 10 integers. Well, x bracket 10 is the 11th integer, so that too is out of bounds. Now, if I run this program, what's going to happen? If I run this program, memory, what's going to happen? Shout it out. No. It's not necessarily. And this is why bugs can be subtle. So all of you who just said psych fault, I was hoping that someone would. That's intentional. So this doesn't necessarily happen to be the case. There are slightly more subtle things going on when it comes to segments in memory. And just because you go ever so slightly outside your own allowed bounds, it doesn't necessarily mean that the program is in fact going to crash. In this case, it clearly didn't. And so it's very easy for programs like this and programs you've written to just overlook memory-related bugs. And in fact, you might not ever detect them until you've actually shipped your software and some user realizes, damn, this program crashed for some reason. Or you run this program again and again and again for longer and longer periods of time, and then finally do you realize that you're sucking up memory even though you're not actually using it. And so there exists this wonderfully useful tool that's available on the cloud. I'm going to go ahead and just copy the command here. So Valgrind is the name of the program. -V is the switch that says give me verbose output, sort of overwhelm me with detail, but some of it helpful. This is a specific flag that says do all possible checks for memory leaks. And then the last argument is just the name of the program that you want to do this memory check on. So I'm going to go ahead and paste this in here, running it on the program called memory, since that's what I named it, and hit enter. And now, unfortunately, a whole bunch of stuff does, in fact, scroll by, all rather quickly. But if we home in on some of the interesting lines, let me go all the way back up here. And it's wrapping a little ugly because of my font size here. But if I scroll up here, notice this. Roughly in the middle of the screen here, there's this invalid write of size 4. So that seems to be happening at some address, which looks like it's an OX. This is something called hexadecimal again. But it looks like this bug is somehow happening on memory.c, line 29, but main appears to be calling F. So in fact, the bug is more likely on memory.c, line 22. So let's take a look at exactly what that is. So let me go back into my program, memory.c, go to line 22, and this is in fact, as you might have guessed, where that particular bug is. So it's not going to be as explicit as it is to say x bracket 10 is out of bounds, but at least Valgrind draws your attention to a specific line of code. It hints at indeed what is the problem. In this case, it has something to do with writing an invalid value of size 4. So that's probably an int, because ints are of size 4 bytes. So you get clues with tools like this and can then hopefully chase down your own bugs more effectively. Well, let's actually run Valgrind again and take a look at a second bug that pops out. And on a smaller screen, this is in fact a little less overwhelming, some of these errors. But let's go here. Oh, interesting. So under leak summary, which is all caps to draw your attention to it, I've lost 40 bytes somehow. Well, 40. So that's 4 bytes for an int times 10, 40. So that already kind of hints at where the problem was. In fact, if you look above, 40 bytes in one block are definitely lost in loss record 1 of 1. Well, again, a little cryptic, but here we seem to have mention of main again on line 29, F on line 21, and then malloc. Odds are, or hopefully, the bug is not inside of the standard C library and malloc, so I'm going to sort of distrust myself more. So memory.c line 21 gives me this blinking line here. And so there's something happening there, this allocation of memory that's leaking eventually, which hints at the fact that you've never in fact called free. So and just as we're preaching now that you start using a tool like this, we'll also start using it ourselves when it comes to assessing your code for correctness. Because we too don't want to look necessarily through every line of code, think through all possible inputs. What better way to sort of analyze your code if other people have written tools with which to facilitate that process? So takeaway here, when writing problem set 5, any of the programs that somehow touch memory, like we're using arrays, using malloc, by all means run a command like that, valgrind-v --leak check equals full, and then the name of your program, and see if you can just skim its output exactly what might be wrong. And certainly reach out to the bulletin board or the teaching staff if you have questions and find some of this overwhelming. But notice I have ignored most of the stuff that's being spit out by the program, and generally that's perfectly okay. Hone in on mentions of your code, especially if it says under leak summary that there's a problem. So, writing quizzes late at night, you get a little goofy, and so there was an allusion to this guy in Quiz 0, and I thought we'd reintroduce him here with a little quick chat about hexadecimal. This is a huge theme of problem set 5, and it also just came up in that output of Valgrind. In fact, GDB too sort of speaks numbers in hexadecimal constantly, so we thought we'd touch on this briefly. And you know, I'll admit that it's a funny thing sometimes teaching a class at Harvard, and you're spending the morning writing a computer science lecture and you actually have to cite sources like toughpigs.com, which is some Muppets related site there. But with that said, hexadecimal. So we talked about binary way early in the course, and even though it might have seemed a little mystical at first, it's really just numbers as you knew them from middle school, but with different bases, with different column values. Instead of it being the ones column, the tens, the hundreds, and so forth, it's instead the ones, the twos, the fours, the eights. Well, in hexadecimal, you have something very similar, but instead the unit of measure is 16. So base 16 instead of base 10 or base 2. What this means is that you have 16 different counting digits. So binary, bi, you have 2, 0 and 1. Decimal, dec, you have 10, 0 through 9. Hexadecimal, 16, you have 0 through F, right? So the world needed some way of counting beyond 9, and so they arbitrarily decided A will be 10, B will be 11, ... F will be 15. So what does this mean, and why is this actually useful? Well, hexadecimal is useful in that you have 16 possible values, or 16 possible digits, which means you can essentially represent, this is going to be a very space-constrained lecture with no eraser, do it the old-fashioned way. This is not going to be good. All right. Feel free to volunteer an eraser if you have one on you. Hexadecimal. So we have a number in, let's say, hexadecimal like 0x01. All right. So hexadecimal digits only require 4 bits for representation. Right. Because if you have 16 possible values, that's like 2 to the 4. So that implies 4 bits. So if I wanted to represent this hex value, which is just 0 in decimal, and 0x01 in hexadecimal, or really 01, or if you really want to be particular, just 1. The 0x is just notation, meaning here comes a hexadecimal digit. What is this same value in binary? Oh, and this is, see, if only I had an eraser. This is 0, 0, 0, 1. All right, by contrast, let's fast forward. 15 equals 0x f. All right, so f is 15. So how do I represent 15? Yeah, so 1, 1, 1, 1. So that's a 1, 1, a 1 plus 1 in the 2's column, 1 in the 4's column, 1 in the 8's column, and that indeed adds up to 15. All right, so that makes sense. So now if you start appending numbers together, if I really wanted to be particular, because I said 0, 1 here and not 1, 1, that's implying that there's 2 hexadecimal digits. So this guy sort of takes up 4 binary digits for representation. This guy, how do I represent him in binary? Well, that's easy, right? 0, 0, 0, 0. So now let's get slightly fancier. If you have a number like 0xFF, all right, so FF, that's in binary, that's going to be what? So 1, 1, 1, 1, followed by 1, 1, 1, 1. Well, what is that number? Well, that's 255 in decimal. And so you have just this very basic building block. So a hex digit typically takes up 4 bits. You can represent that digit then with those 4 bits. If you have hex digit, hex digit, hex digit, you just concatenate those bits together, and you can sort of do the math and figure out what the decimal equivalent is. But this does kind of beg the question, since we seem to be adding unnecessary complexity, why bother using hex at all if we already have decimal and we already have binary? Yeah? Yeah, so it's a convenient way to represent a byte. So a byte is 8 bits. Oh, thank you very much. So a byte is 8 bits. And so if you want to represent 8 bits, you can represent it as 4 bits followed by 4 bits. And hexadecimal is conducive to that because each of these represents 4. But OK, so what about decimal, though? I mean, decimals kind of work pretty well for my whole life. Why do I need hex, really? OK, so it doesn't translate directly to binary by way of digits. So this very straightforward mapping whereby each digit in a hexadecimal value can be mapped to a binary value indeed isn't so straightforward in decimal. And what else? You can actually be much more succinct. It's no accident that all of these programs like Valgrind and GDB tend to use hexadecimal all over the place, because if you have 16 digits instead of just 10, and God forbid just 2, you can actually sort of collapse your values into much shorter strings because you can pack more bits into each digit than you can with, say, decimal. So in the world of computer science, hex is common, decimal is common, binary is common, and you even see octals. So if you want to read up on octal and read up on the chmod command, which you might have seen in a problem set or seen a TF use, that too is very much related. But there are some interesting issues that result now from use not of hexadecimal per se, but some confusion can arise by expressing numbers in hexadecimal. And this even comes up in problem set 5. So in the world of computers, there was, say, a debate years ago as to how you should represent multi-byte integers, multi-byte values in memory or on disk. So if I wanted to represent, let's say a number like, faking out the lights here. If I wanted to represent a number like, what's the number, 58, let's see what the implications might be. So let me go ahead and open up this program, endian.c. So endian refers to which end of a number are you storing in the lowest address in memory. That's going to sound completely cryptic. Let's do this by way of example. So it turns out that in a CPU that is big endian, as in the case of the figure on the left, that computer lays out a 4-byte value from left to right, or rather from low memory address to high memory address. So sort of in the way you would expect to write it down. So typically when we've been drawing pictures on the board saying that something's in memory, even I typically write from left to right, top to bottom. Or even in the case of the stack, we still tend to go left to right. So in this picture here, what this is saying is in the box labeled register, a register is just a 32-bit value inside of most CPUs. It's sort of the smallest unit of memory that the computer manipulates at once. When you have a 32-bit architecture, that means essentially that your registers, the tiny pieces of memory inside the actual CPU, are 32 bits large. So suppose that your CPU is storing the value 0A, 0B, 0C, 0D for whatever reason. Well, if that value in the register is then stored to disk or stored in RAM, as would be the case when the CPU is done touching that value or generating that value, it is literally going to be plopped into RAM or on disk from left to right, just like you would print it out character by character or digit by digit. So sort of very straightforward. Unfortunately, most of the CPUs you guys use are what are called little endian, whereby the little end of the number comes first and not last. So again, on the picture at the right here, notice that 0D, which is the littlest number in this 4-byte value, right? Because the numbers all the way to the right are the slowest ordered bits, and the column headers get bigger and bigger as you go from right to left. Well, notice that 0D is actually being stored at the end of memory. So it's the little end is being stored at the end, whereas the big end, that is 0A, comes first. Now this is sort of consistent with the way you would think numbers are represented. The problem is that most computers, including your PCs and Macs these days that run Intel x86 CPUs, take a little endian approach, whereby the least significant byte, that is the bytes in the smallest columns, so to speak, the ones columns, the twos columns in that sense, are actually stored first in memory. So 0D instead gets laid out first in RAM or on disk, followed by 0C, followed by 0A. So it's as though if you have this 32-byte value, such as something that looks conceptually like this. If this is a 32-bit value, well, this is a 4-byte value, so that's as though it's 4 separate bytes. This is what it looks like to us conceptually, and this is what it looks like when it's actually inside the CPU's register, that tiny chunk of memory. But when you actually store this value on disk or in actual RAM, what happens is this guy goes there, this guy goes there, this guy goes there, and this guy goes there. Which might seem a little strange because that looks like an awful lot of crazy work for no added value. But it's really just that we're thinking of the world upside down. You can sort of view the world of little endian as being perfectly consistent with reality if, sort of like we tend to do with the stack, you just flip memory upside down and say you're counting from bottom up instead of top down. So this is really just a convention. There's nothing technically interesting about this, but the problem is that it leads to very subtle bugs, or at least confusion, even in problem set 5. So this is a program, endian.c, whose sole purpose in life is to demonstrate this. So recall in problem set 5, if you've dived in, which according to the cloud, about 200 of you have. So that's good. Let me go to cs50.net, problem sets. Go to standard edition. And all I want to do briefly is pull up that little chart that we whipped. If you're wondering why there's a naked George Costanza on the front page, ask someone who took the course last year. All right. So this is the picture we drew in the PDF. So remember that a bitmap, and if you've not tuned in yet to problem set 5, that's fine. Just know that a bitmap, BMP, is a graphical file format that's very, very simple in its underlying implementation. The first several bytes of a graphical file in the BMP format has what's called a header, which is a sequence of bytes, each of which has some special meaning. For instance, per this PDF, the first 2 bytes in a bitmap file is by convention called BF type. And that is a hard-coded value, a magic number, so to speak, that must be present in any BMP to sort of tell the world or hint to the world that I am a BMP, so that a program can just look at those first 2 bytes and guess with high probability what kind of file this is. But we're going to focus for now on BF size, just because it's very easy to wrap one's mind around. So it looks like starting at byte number 2 in the file, going up to byte number 6, that is 4 bytes total, there's this field called BF size. Now I chose this 4-byte value because even though you'd like to think that the size of a file represented in binary is sort of laid out on disk in the BMP file from left to right, from high-ordered bits to low-ordered bits, what you're going to see is actually it looks like this, which unfortunately causes undue confusion, even in 2-byte values like BF type. And that even was a question that came up on the course's bulletin board already. So let's see what this program does. First, I'm going to spoil what the output is. Make endian. I'm going to run endian now, and notice that it just does nothing if I forget the name of the file. But then I whipped up this tiny little bitmap file. So dot.bmp is literally a 1 pixel by 1 pixel bitmap that just has a red dot in it because I just wanted the smallest possible BMP file. And in fact, if I do an ls-l for the long listing, notice it's 58 bytes, which if you've read the spec is pretty consistent with what you should expect because every BMP has a header that's how big? 54 bytes. And even though, wait a minute, this is just a 1 pixel by 1 pixel value, you have that notion called padding. Again, if you've not read the PDF, this will soon make sense. So we need to pad it up to a multiple of 4 so that 1 pixel becomes 4 pixels in disk. So that's why we have 54 plus 4 equals 58. So that's why this is sort of the smallest possible BMP that we can represent that actually is an image. So let's go ahead now and run endian on dot.bmp, and notice that this is all this program does. It's sort of a quick and dirty diagnostic program that's just telling me 3 different times, and in several different formats in one of them, what is the value of BF size. All right, well, let's take a look at this program. It looks like the first couple of things I do are some sanity checks. Make sure that you're running it with 2 arguments, the name and the file. Then go ahead and use fopen to open argv1, which is the name of the file, in what's this mean? Read mode, so that I won't risk changing the file. Now I'm checking for null just to make sure I didn't screw up and run it with a bogus file. But if I get to this point, notice what I'm doing now. fseek is a function that just moves the reading head, so to speak, somewhere within the file. So up until now, I think every program we've given you that involves file I/O, and there's not been that many, pretty much reads the file from left to right, and that's it. But it turns out, just like you can sort of move back and forth on a CD, on a record, and a cassette tape, so can you move back and forth in a file. In fact, thinking of a file on disk as a cassette tape is probably a reasonable analogy because you have to seek from one location to another, sort of fast forward and or rewind to move around. So fseek is like fast forward in this file called fp, our file pointer, 2 bytes inward from this special value. So seek_set. is just a constant that I found in the man page that says this is the special constant that represents the start of the file. So that call to fseek means start at the start of the file, move 2 bytes in, and then wait for the user to do something interesting. Well, what does the user do? Well, I declare an unsigned long, because size can only be positive. So I went ahead, or non-negative. So I said unsigned long. BF size is the name that I'm going to give to this variable. And then I'm doing this line. So fread, where am I reading? I'm reading into this variable. So if I'm changing the variable, I have to pass it by reference. How big is this variable? Well, I'll just do size of BF size. But quick sanity check, how big should an unsigned long be on this architecture? A long? How big is a long? This is one of those sort of potentially trick questions. It's someone put a stake in the ground. 8 bytes? I heard 4. I'll go with 4. So a long is 4 bytes, right? Longs, unfortunately, are 8 bytes. But a long, like an int, is 4 bytes on a typical x86 architecture, a typical PC or Mac today. All right, so this means read in 4 bytes. This field here just means how many BF sizes do you want to read in case you're reading in an array's worth. Well, I just want to read in 1. And then where do I want to read them from? This file pointer. So this use of fread you've seen before, certainly in this week's distribution code, if not in other contexts. So now the very first thing I do is I just tell the world what BF size is. I'm just printing out what I read from disk. So hopefully it's going to say 58. Next, I'm going to rewind my file to the beginning, just so I can start this process over again. And then just to show you sort of at a low level what's really going on, I decided to take a sort of more technical approach. I just want to malloc this time 14 bytes because I just want to suck in from disk the first 14 bytes. I don't want to treat them as fields. I don't want to assume that one's an int, one's a short, one's a long. I just want bytes, byte after byte after byte, and 14 of them. To do this, I use malloc, and I'm pointing it at a char star buffer. By convention, it's not a bad thing to use unsigned chars for weird corner cases, but up until now, you guys have probably just used chars, so let me wave my hand at that detail for now. So fread, read into this buffer 1 char, or 1 byte, and how many of those? 14. Now you can technically swap the 1 and 14 here. It's just how you view the world. Half empty, half full kind of thing. You're either reading in 14 of something that's 1 byte or 1 of something that's 14 bytes. It really doesn't matter so much in this case. So what am I doing next? Well, here's some cryptic syntax, but a wonderful quiz 1 question. What is this doing? Well, I claim that this is also going to print out BF size. So what is buffer? In a sentence, what is buffer right now? The address of what? What's buffer? Someone more assertive and louder. What is buffer? It's the address of the 14 bytes that I just malloced. So it's the address of the first of 14 bytes that I just malloced. So buffer plus 2 is that little trick called pointer arithmetic. It's just moving my pointer to the address of the second byte of the 14 that I allocated. Now, what should live at that second byte onward? BF size, right? Notice that from this PDF alone, I know that this field is 2 bytes into the file. Well, if I've sucked into memory the first 14 bytes, I really only care about bytes 2, 3, 4, and 5. So how do I get at those? Well, this gets me to the start address. But now this is like saying, OK, here's a pointer to the address of the second byte in this buffer that I've allocated. How do you go about slurping into memory, slurping into a variable, in fact, 4 of those bytes? Well, you have to do a trick like this. Buffer right now is technically a pointer to a char star. Now, a char is how many bytes? So it's 1. So what this is implicitly saying at this moment, here is a pointer to a single byte. But I need to sort of trick the computer into thinking, here is the address of the first of 4 bytes. Here is the address of not a char, but a long. So that the compiler for me slurps in not just that byte at that address, but that byte plus the 3 after it, because I'm telling it what actual type is being stored there. So I cast what was an unsigned char star to an unsigned long star. Now how many bytes is a long? 4, so this cast, and now we're finally using casting for something that's a little more sophisticated, is telling the compiler, go to this address, but think of it as the address of a long, not the address of a char. So the effect of that is going to be that the computer returns to me a value that's not at that specific byte, but a value that starts at that specific byte and bleeds into 3 more to the right of it so that I get back a 4-byte value. What do I do when I get back that address? Well, I go there by way of this dereference. So in other words, this cast tricks or tells the compiler, treat this pointer as pointing not to a single byte, but to 4 bytes. And then this dereference operator says, go to the value at those 4 bytes. And then, of course, we're using printf, so it just gets spit out on the screen. And %LD, recall, is just the format string for a long decimal, so a long value. OK, finally, let's focus in on this. So print individual bytes in decimal. Well, this one's easy, actually. So now I'm printing once more bf size, and I'm printing int, 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 int. What am I printing? Well, it looks like I'm printing what's at buffer location 2, location 3, location 4, and location 5. In other words, if this is bf size in memory, I'm printing each of these values out at once, just because I want to see what's at each individual byte. OK, and finally, even though I know this is a lot of detail, this is a little line of code that's pretty slick, if I may say so myself, that converts a byte into binary aesthetically. So using some special tricks called bitwise operators, we are actually converting what is a byte of 8 bits and displaying them as 1s and 0s. So again, to remind you what the point of this was, it was to generate output like this. So for now, I'm going to wave my hands at that for loop and say that it converts, or it shows you the binary values inside of a integer. All right, or inside of a byte. All right, so what happens here? So notice that not only have I printed out bf size in decimal using decimal, 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 I'm also just using a printf trick. %x is hexadecimal, 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 hexadecimal. So this is just going to print out what's in those first 4 bytes in 2 different bases, decimal and hexadecimal, and then this loop prints it out in binary. So let's take a look at what happens. So if I run this program again, what I get is this output here. So this is to be expected. This is when I just slurped it into memory using fread and I read in an actual long. So that was easy. This one uses that pointer trick. And because I cast that single address to an address to a long, that also gave me back those 4 bytes. But here now is the conundrum. Notice that bf size, if I actually print out buffer bracket 2, followed by 3, followed by 4, followed by 5, what I actually am getting is not the value 0, 0, 0, 0, 0, 0, and then the equivalent of 58. So the bits representing 58, what do I appear to be getting instead? 3a is in hexadecimal, 58 in decimal. So what's happening? So at the lowest ordered byte is actually the number 58, aka OX3A. So what this hints at is that if you actually look closely, byte for byte, at what's on disk or even what's in RAM, you can see the little endianness of the underlying computer. But the other 2 approaches we took, which were to rely on the compiler to figure out how to read something into memory, for instance, this call to fread, sort of seems to have dealt with the endianness for us. And even this trick here using pointers seems to have dealt with the endianness for us. But if you actually dive in byte for byte, as some of you already have in problem set 5, and actually look at individual characters, you have to beware that they're not necessarily going to come out in the order that you expect them. And so what we see here, to be clear, is that even though you would expect the number in memory, the size of this file, to be a whole bunch of zeros, because a 32-bit int is huge, a whole bunch of zeros followed by the bits representing 58, it turns out that those bits are actually way up here in reality instead of where you would expect them to be conceptually, which is here. And so that is what endianness is all about. And unfortunately, it causes confusion, even though it's really just a convention as to where bits are laid out in memory. So that was a huge lot of scary detail. Let's take our 2-minute break. OK, we're back. So one more piece of low-level detail, if you don't mind, since this will be useful in the long term. C supports a bunch of operators called bitwise operators, which are related to this stuff we just did, because in fact I use these operators to convert each of those 4 bytes to a binary form, just by spitting out zeros or ones conditionally. So if you have 2 variables, say 2 chars, which are really just bytes, and you do char1 and char2, that is the ampersand, what you get is not a Boolean operation. Because recall, for the Boolean operators, we had ampersand, ampersand, and we had vertical bar, vertical bar. If you instead just use one of these things, they don't do a Boolean operation, but a bitwise operation, which, as the word suggests, operates on each of the operands, the left one and the right one, bit by bit by bit by bit. Or just didn't need the last one there. So what are the operators that are supported? You can AND bits together, and we'll see what that means in a second. You can OR them together. You can do something called exclusive OR, aka XOR. You can complement them with the twiddle, which just means flip the bits. A 0 becomes a 1 becomes a 0. And then you can shift the bits from left to right or from right to left. And each of these actually has a great number of uses. Really quickly, let's just think conceptually about what these mean. So as the word AND kind of conjures up, for 2 bits, A and B, to be a 1, both A and B have to be a 1. So this is a truth table, so to speak. And what this means here is that if A is a 1 and B is a 1, then A and B, A ampersand B, is also a 1. But each of these boxes would take on a value of 0. Because 1 and 0 is not both true, so you get a 0. 0 and 1 is not true. 0 and 0 is certainly not true. Only 1 and 1 is true. All right. Meanwhile, for OR, well, if you have a 0 or 0, is either of them true? No, so you get back a 0, aka false. What about a 0 or 1? So A is 0, B is 1. 0 or 1? True, so you get a 1. 1 or 0, same thing, just flip, so that's a 1. How about 1 or 1? What's the truth value? Sure, right? That kind of is like a Boolean value. Either this is true or this is true, so the whole thing is true. So there is a relationship here, but it's operating in a bitwise sense. Well, what about XOR? XOR, as the name kind of suggests, exclusive OR means one of the bits has to be a 1 and the other cannot be, or vice versa. So you have exclusivity. The bits are not the same. So 0 XOR 0 should be what, per that definition? So a 0, it's false because they are not exclusively different. So one's a 0, the other's a 0. That's not exclusive. What about 1 or 0? Well, that works. 0 or 1, that works. 1 or 1, that doesn't work. It's not an exclusive thing. Now this one's easy. What's the complement, aka 1's complement of the number 0? Well, that's a 1, and 0 complemented becomes a 0. So that means that is to say flipping bits. What does it mean to shift bits? Well, this is kind of a neat trick, actually. If you have a value like this, if I do int I gets 1, so I have a variable I called 1, and now I do this, I gets I left shift, so angled bracket, and the number 1, as this sort of syntax kind of suggests, that means take whatever value's in here and shove it to the left by 1 place. So shift the bits by 1. And so what does that give us? Well, if we think of I, just for simplicity, so I don't have to write out 32 bits, let me just write out, say, 4 of them. 1 is actually 0, 0, 0, 1. But if I left shift these bits, that's like sending all of the bits that way. So that actually becomes 0, 0, 1. And then the shift operator pads whatever gaps it made with a 0. So there's this neat implication of this. What's another way of describing? So what is this value? What's 1 left shifted by 1? What do you get? 2. What if I do it again? What do you get? 4, 8, 16. So you have this really neat multiplication operator built in for multiplying a value by 2 again and again and again. So there's some notion of exponentiation there too, by a power of 2. That's sort of an implicit trick of using bitwise operators. I used it for a different reason. I used it to create what's called a mask. more generally. So bitwise operators, especially the left shift operator, is very useful if you want to take some value and look at individual bits in that value, because you care about checking, is that bit a 1, is that bit a 0? Now in this case, I absolutely care about which bits are 1 and which bits are 0, because the whole point of this last loop in that program was to spit out an ASCII 0 or an ASCII 1 so that I could see the bits. So this sort of begged the question, how do you iterate over a byte, which is 8 bits, 1 by 1 by 1, and figure out if that underlying bit, which C up until now has not let us look at individually, you can only see entire bytes, not bits, well, bitwise operators, namely this guy, the left shift operator, by using it to generate what's called a mask, can we actually introspect individual bytes and see what's inside of them, see what's inside of their 8 bits. So notice what I'm doing. Ignore this loop here, because this loop for now just iterates over all 4 bytes. Let's just focus on the inner loop, which is just 1 given byte. So notice what trick I've employed. I've initialized a variable to j, called j to 7. Now 7 is going to be the number of places that I ultimately shift a hard-coded value called 1. In other words, notice here that my mask in this line here is essentially initialized to 1. So I have an int that's called mask. It is in fact 32 bits, but again, that's sort of a uninteresting use of time to draw those all out. So really, I'll just draw a few of them. Let's say 8, because I'm only actually using 8 of them. So if I've got 8 bits, and they're representing the number 1, because again, int mask gets 1. That's like saying 1, 2, 3, 4, 5, 6, 7, 8. So that is the decimal number 1. But if I now left shift this value by j, by how many bits do I initially shift this value for the first iteration of that inner loop? 7, right? So that means like this 1 becomes 1, 2, 3, 4, 5, 6, 7. So 1 left shift 7 gives me what? Well, 1, 2, 3, 4, 5, 6, 7. In other words, it has the effect of moving that 1 all the way up to the highest bit place. Well, what am I now doing with this mask? Well, that number actually equals what? The number, what, 128 if you figure out the places? But that's uninteresting. What I really care about now is treating bits as just bits, zeros and ones. But notice I'm using this other bitwise operator. If the current byte in the buffer, so this again is the outer loop, so if the ith byte, byte number 2, then 3, then 4, then 5, if that byte bitwise ANDed with this mask is true, because it's in parentheses here, what am I going to print out? An ASCII 1. So what does that mean? I'm saying if, let's say my number is, just to be argumentative, suppose that I have that in my byte. It's a whole bunch of 1s. So my goal is to print out 8 ASCII 1s because that's what's in there. Well, let's see what happens. Here's my mask. And what that line of code parenthetically is saying is if buffer bracket I, if this thing, ampersand mask, this thing, is true, because it's parenthesized, I want to print out an ASCII 1. Well, let's just draw this mathematically. This value here is 1, 1, 1, 1, 1, 1, 1, 1. Okay, so now what operator am I using? The ampersand operator. So that's like drawing this if we take the grade school approach. And now it's bitwise, this operator, which means it looks at every bit in this value again and again and again against the corresponding bit in the other value. So 0 and 1, 0, 0 and 1, 0 and 1, dot, 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 1 and 1, yes. And so what you get out is this really big value, in fact, the same value that you started with, but this value, is it true or false, so to speak? It's true, because it's non-zero. And this is why it's useful to have this reality that any non-zero value is true. What I've essentially done with this parenthetical is just say, if the result of ANDing, bitwise ANDing, the number with this mask, gives me any 1 bits anywhere such that the end value is a non-zero value, well, what's the implication? That there was a 1 there, and so I want to go ahead and print a 1. Otherwise, I want to print a 0. Yeah?
If 0 represents false in C, why do you generally return 0 when a program works?
It's a good question. So we seem to have this paradox whereby if 0 generally represents false, why do we typically return false when actually something good happened, like a program terminated correctly? A program let's argue, can only work right in one possible way, because it either works or it doesn't work. But if it doesn't work, there's an infinite number of things that can go wrong. In fact, up to 4 billion possible things that can go wrong. And so that's why you use non-zero values to signify error. Gives you a whole lot of room for mistakes. So back to this. We won't do all 8 iterations because they'll very quickly become clearly identical. Suppose now we do one more iteration. J minus minus means that this story changes how? I instead shift this value by what? Not 7, but by 6. So 6 means this guy goes da 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 here. So we only get as far as here. Now I have this mask. So again, notice that mask variable is sort of a temporary variable that I'm using to look at, to introspect individual bits. And it's a mask in the sense that if you kind of have fun with your mind's eye here, you can sort of lay this on top of the byte in question, and only the bits that shine through, that are both a 1 in the mask and a 1 in the value, actually pop through into the end result. And so here we get back this answer, which also has at least 1 bit in it, which means it's not false, it's true, and so we again print out a 1. So using these bitwise tricks, can we actually look at individual bits for this, for kind of a fluffy application, just printing something out aesthetically in binary. But this is hugely useful when you're actually using individual bits for more technical reasons. In fact, many of you have probably needed to represent the notion of true or false in a program before, and so you might have had an array of Boolean values. Right? What's unfortunate, what's dumb about using an array of bools, do you think? Well, what is a bool? We've never really showed you. We've just given it to you for free in the standard bool library. But a bool is a byte. It's like an unsigned char, which means the world, because C operates at the byte level, you're wasting 7 bits for every bool you ever used in your life thus far. And that's wasteful, especially when this array is large. But what this existence of bitwise operators sort of hints at is that there are more space efficient, more clever ways of representing the notion of true or false that actually leverage each and every individual bit rather than wasting them just because your language C doesn't let you individually allocate bits. So you do have some recourse here. So if you'd like to see more on these bitwise tricks, take a look at 2lower.c and 2upper.c in your printouts or as an at-home exercise, and you'll see just kind of a semi-clever way of capitalizing or lowercasing a number by turning on or off the 1 bit that distinguishes uppercase letters from lowercase letters. In fact, just to put a context around that, you know that capital A in ASCII is what number? 65, and lowercase a is 97. So if you really want to be a geek at home, go ahead and write down the binary equivalent of 65 and write it down left to right and say this is capital A. Then below that, write out the bits that represent 97, and next to that, write lowercase a. And if you look at all of the individual bits, you'll notice that they differ in just 1 place. So there's only 1 bit, the 32s column, in fact, that distinguishes an uppercase letter from a lowercase letter. And that was intentional, presumably, on the authors of ASCII's part, because it allows you to, they look almost identical underneath the hood. And so these 2 programs we whipped up, 2lower and 2upper, simply flip that bit on or off if you want to force something to lowercase. You don't have to do any of those casts and addition and subtraction that we did a while ago. And if you really want to be a geek, this too I'll sort of leave as an at-home exercise. I promised weeks ago that you do not need a temporary variable to swap the values of 2 variables. Up till now, we've had 3 steps. 1, you save 1 value in a temp, then you clobber 1 value, then you grab the old value from the temp and put it in the other one, and you're done. But it turns out, as I promised, you can actually sort of conceptually take 1 value here, 1 value here, and using bitwise operators, namely the XOR operator, you can sort of do this, where you gradually swap them such that some bits seep into the other and some bits seep into the other, and then with your final statement, voila, you've cleaned everything up and you've moved 8 bits from the right to the left and the left to the right without using temporary storage. And so these 2 slides here demonstrate using 3 statements, 3 uses of XOR, this code here, how you can actually swap 2 values variables using only bitwise operators. It's not necessarily the sort of thing you need to or should use necessarily, but it's really neat because you can see what's going on underneath the hood. And that's what all of these comments for. It's sort of like the backstory as to what's happening with each simple line of code. Whew. Okay. so now we sort of went down here with all these very technical specifics. Now we come back up here and try to solve real world problems and have a means of tackling problem set 6, which again will be to implement the fastest spell checker possible, but it will be largely to you to design that piece of software. In fact, you get very little of a framework in terms of code that we have written for you. So let's consider now some more interesting data structures than we were allowed last week. So back in the day we had arrays. Even in Scratch we have arrays in the form of lists. The problem with an array though, give me one problem with an array. Let's motivate this. I heard it's a fixed size, right? So you have to sort of decide at compile time, maybe on the stack, exactly how big you want that array is. And if nothing else, it's a pain in the neck to grow an array because you have to write lines of code to do it. And even if that's sort of not daunting, you have to waste CPU cycles to do it because you have to you have to create a new buffer. You have to then copy everything over. You have to free the other buffer. And that just adds up again and again and again. It's just not a very nice data structure, it seems. All right, so then we had lists. So singly linked lists allowed us to grow our data structure dynamically. And what was a downside, though, or a cost of that? So memory, and what do you mean? Good. So it's a little more wasteful when it comes to memory because now we have metadata. We have pointers that link this thing together. So if you're just storing integers, you're kind of using twice as much space because this pointer is the same size of an integer. Now, fortunately, if you're storing bigger objects like student objects or things that are more interesting than just an int, maybe using an extra 32 bits per data structure, not such a big deal. But arguably for smaller data structures, not ideal. Other downsides of a linked list? Yeah. Exactly. So you give up random access. So arrays are randomly accessible by way of their indices. You can jump to any location in constant time. By contrast with a linked list, how many steps maximally does it take to get to, say, the end of the list? Big O of n, right? You sort of have to go all the way from left to right just to reach the end. Now, we did see a hint at the end of last week's lecture, well, you can maybe have some additional metadata. You can maybe have arrows going in both directions. Someone, I think, suggested circularity. Maybe it was me accidentally. So you can sort of chip away at some of those things, but asymptotically, it still takes big O of n to reach, say, an arbitrary value in the middle, especially if the list is long. So you gain something, you lose something. And that, again, is this recurring theme in CS whereby you rarely, if ever, get anything for free. But we promise to do better than these fairly naive data structures like arrays and lists, because what was bad about them was this constant time lookups and constant time, linear time insertions and linear time deletions and linear time lookups. Like, that is not good when n is large. So we promise something amazing. Constant time lookups and constant time insertions. And we get those kind of with this thing called a hash table. So suppose that we needed to maintain in memory a data structure for a whole bunch of students, and the students all have unique IDs. And these IDs are just integers. Well, I don't know necessarily in advance how many students I'm going to have to keep track of because the university admits more and more students every year, but I don't want to pre-allocate, say, 4 billion student records because otherwise my program is going to take up a ridiculous amount of memory unnecessarily. So how do I go about representing all of these students? Well, in the world of an array, I could just allocate, for instance, an array for like 6,500 students. So an n equals 6,500 because that's roughly how many undergrads we have. Maybe I can give myself a buffer and say, you know what, let's at least plan 4 years ahead. And let's say that, you know what, this should really be like 13,000. Well, maybe let's just try to postpone dealing with this problem and say it's 100,000. But either way, we draw the line in the sand somewhere. And we say this is how many students this array can fit. The problem, though, is that it's not necessarily clear where we should put these students. So if we make a buffer that's larger than the number of students we actually need to insert, where do we go about putting the student with ID number 1? Just for the sake of discussion. Where would you put them? Well, let's put them at the beginning, right? This array is initially empty. So let's put a student object looks like this. Let's put essentially a pointer there or put the student record actually there. So this is the student with ID number 1. And let's just say now for the sake of sanity, 1, 2, 3, 4, 5, 6. So n is going to equal 6 for now. just so that we can draw fewer boxes. Now I have a student who's got ID number 2. OK, so pretty simple. Why don't I drop him into the second spot here? But now, because for security reasons and other purposes, your ID numbers freshman year are not assigned using the ++ operator, right? You and your roommate don't have ID numbers that differ by 1. There's some kind of scheme, some kind of algorithm that's used so that you have sparsely allocated ID numbers at Harvard. So there's gaps between people's ID numbers. So turns out that the next student who comes to campus, not going to get the number 3. They're going to get the number 7. So where do we put them? Well, 1, 2, 3, 4, 5, 6. OK, damn, problem. Right, so obvious solution, reallocate the array, grow it, ... But that doesn't seem necessary yet, does it? So what could we do with student with ID number 7, because the obvious mapping for him onto this array doesn't seem to fly? What's that? A new array? So I'm saying that seems silly, right? Because I have all this space, and yet 7 just really has to go there? It doesn't feel like that's necessary. What else could I do without allocating more memory? Or put it in the, so in the third space, right? So, OK, this was nice and convenient and kind of seemed like the answer David wanted. But why don't we just say, just go left to right and plop that student in at the next available location? And it was just a coincidence in retrospect that 1 went in slot 1 and 2 went in slot 2. Well, 7, you know what, is going to go in slot 3. And so now we can continue to allocate these numbers in this way, ... And that's nice and easy. It's straightforward. In fact, what's the running time of the insertion operator given this approach? Big O of, so I heard big O of constant. So constant time, what else might it be? Linear. So herein lies assumptions. If I'm not remembering anything about this array, absolutely, it takes how many steps to find the first available spot? Big O of n, maximally. But I can be slightly intelligent here, and I can spend 32 bits, an int, and actually keep a temporary variable, or rather a permanent variable, pointed at the next available location, or equivalently, the last allocated location. So think about the sort of implications of this. Just by spending 32 bits, keeping around one additional int, an index value, can you avoid having to do a linear algorithm just to insert? Just update this guy in constant time. So herein lies sort of an instance of design. Like that is such better design, arguably, certainly for large data sets. Spend one more int and you get a huge performance gain because you don't have to skim the list again and again from start to finish. But there's still a problem. How do I find number 7 now? What's the algorithm with which to find an arbitrary student, for instance, number 7? Sorry? What's the running time of that? It's kind of linear, right? Because it was just sort of a nice thing that I kept track of where 7 goes, but there was no fundamental, say, mathematical relationship between the ID number and where he ultimately ended up. The downside of that is it's really hard to find that thing again without having remembered in, say, some auxiliary structure where 7 went. In other words, yes, I was keeping track of where 7 could go, but that was completely arbitrary with respect to the number 7, the ID value, the key value that I up until now had kind of been using. So to find 7, it really kind of takes linear time. I have to start from the left, move all the way to the right until I find, or don't find at all, number 7. So that's not ideal, but what this is kind of an example of is, and so just to introduce some jargon that will recur, at least if you take future courses in data structures like 124, I kind of have to probe, so to speak, the array to find this value, checking this array, this element, this element, this element, trying to find the value in question. And it's a linear probe because it's left to right, checking on each time. But what if I'm a little more clever? Rather than, let's see if I can do better, rather than just drop 7 into the most recent, into the next available location, give me something a little algorithmic, some process that I can repeat the next time around when I need to go find that guy. And let's leverage, for instance, his number, which again will be 7. Ooh, so mod, right? So even though mod was maybe this strange operator early on, he has many, many wonderful uses. So mod gives us options. If I take any ID number, mod 6, what range of values can I get back? 0 to 6. That's perfect, because now I sort of have a deterministic place to put number 7. What is 7 mod 6? Okay, damn, like we didn't quite solve the problem. He wants to go here again, assuming this is 0, this is 1. So we'll go back to 0 indexing. So what can we do here? Well, maybe the first obvious approach is let's just drop him in the first spot next to the place that we ended up. So this is what linear probing really is. You use some kind of function, what we'll start calling a hash function, which takes some input, like an ID number, and magically outputs an index location using that number. And maybe that hash function is as trivial as ID number mod total size of the array. That's perfectly legitimate if simplistic. Well, if that space is blocked, linear probing, this algorithm called linear probing, would have you say, okay, try there. If the space is already full, probe not from the start of the list per se, but from wherever you ended up, going from left to right until you find a spot. Now, in theory and asymptotically, this does not change the running time. And if you sort of think through the implications, you could still have a linear time lookup and a linear time insertion. But in the real world, we don't always care about asymptotics. We don't care about the worst possible case, because the worst possible case doesn't happen all that often. More likely is that, you know, there might actually be a bucket that's empty pretty close to where this hash value is, which should be here. And in this case, absolutely, there was. So we kind of got lucky. So again, you'll see this tension too between theory and practice, where it helps to sort of think about your world in terms of big O and omega and such. But at the end of the day, if you're writing software where the human cares about the performance, you might not care about mathematically what the implications are. But there is a gotcha here. Suppose that just because this program's been running a really long time, well, 7 might end up, because there's someone there, 7 might actually end up at the end of the list. And in the real world, that too, not so good. So that kind of begs the question, especially since this approach was so relatively easy to come up with, can we do better? Well, first let's ask, why? Like, who cares? Well, what we've just seen is an example of what's called a collision when it comes to data structures and the storage of data. I took an ID number, I performed a function, a hash function on it, and that gave me a hash value. All right, unfortunately, that hash value put me in a place where there's already some other value. So I had a collision. So let's ask ourselves, what's the probability that this is ever going to happen? Because if this is not going to happen all that often, then who the heck cares that I, in this contrived lecture example, bumped into a collision? Maybe in the real world, it's not really going to matter all that much. Well, we can frame this by way of what's generally called the birthday problem. So there's about 300 students in this class. So it kind of makes sense that, you know, given 365 days in the year, 300 students, there's probably going to be at least 2 students with the same birthday. And we're not going to do roll call, because we can actually model this mathematically. If you assume that sort of pregnancies are uniformly distributed over the course of a year, and therefore you have a random uniform distribution of birthdays throughout the year, we can model this with a fairly simple formula. In a room full, such as this, of NCS50 students, what's the probability that at least 2 of you have the same birthday? Any old birthday, because the relation here is that suppose our array is of size 365, and I, one by one, ask each of you what your birthday is and your name, and I plop you and your name into the appropriate index in the 365 length array. The question we're asking is, with what probability am I going to have to put 2 of you in the same box? Are 2 of you going to collide? Well, it's the same issue as this hashing problem, and this is the way of looking at it mathematically. The probability of figuring that out, you can do one of those inversion things where, well, what's the probability that no one has the same birthday? Well, how many birthdays can the first person in the room have without a collision? Any of the 365. So that's 365 possibilities times how many birthdays can the next person have and still not have a collision? 364 times 363 times 362 ... And so if you sort of work through that same logic using the minus signs as appropriate here to sort of flip around what your goal is, you get this formula here. All right, which in and of itself is kind of cryptic looking, but if we graph this, what you see is that the birthday problem is actually rather striking. You can see that in a room full of just, let's say, 50 students, here's the 49th hash mark on the x-axis. If we follow that up, with almost 100% probability, if you have a class of just 40 students, some much smaller humanities class here at Harvard, can you have with near certainty a collision, of birthdays. And you can test this, right? If you really want to be show off your CS50 savvy, go to your next 40-person class, interrupt the proceedings, ask everyone to say their birthday, and with very, very high probability, will 2 of your classmates have the same birthday. And this happens very quickly. I mean, we are way over here. So just probabilistically, with near certainty, is someone in this class going to have it, but even in smaller classes at Harvard as well. So this, we motivated that question with this one, the question of who cares? Well, we care, because collisions, assuming again randomly distributed, uniformly distributed data, is very, very likely. So this example here, though contrived for lecture with ID numbers 1, 2, and 7, is absolutely consistent with the kinds of problems we expect to run into. So there are ways of dealing with this. One is called coalesce chaining, whereby linear probing is kind of bad because your elements get way at the end of the list, potentially. So what if you kind of leave little cookie crumbs around? And this picture, it's drawn top to bottom instead of left to right, is the same idea. If this picture represents a whole bunch of people, and we're hashing on some ASCII value in their name perhaps, or maybe their social security number, something like that, but notice that there are arrows being drawn from person to person. What's a little more clever, if we care about speed when it comes to finding number 7, suppose that again, this was the state of our world a moment ago. This cell was filled, so is this, so is this, so is this, so is this, but this is empty. I'm trying to insert student number 7. I hash to this value using my hash function called n mod 6. That puts me here. Linear probing would have me go da-da-da-da-da-da-da and end up there. But again, there was no sort of cookie crumb trail that wrong analogy. No breadcrumbs that led me to that new location. So what coalesce chaining is all about is about maintaining a little extra memory, maybe an extra array of pointers that allows you to, yes, try to hash here, but if that fails, go do probe when doing the insertion and put 7 there, but add a breadcrumb from the place you tried to go to the place that you ended up, so that the subsequent lookup time for the number 7 takes how many steps in real terms? So I end up there. How long does it take to follow a pointer in memory? It's constant time. So now I've whittled down O of n to just 2 steps, potentially. And again, the astute will notice that, wait a minute, this could still kind of devolve into linear if you're chaining again and again and again, as this picture actually hints at. Because what if you actually hit a collision elsewhere down the road? So it's not perfect, but we do ultimately have an even more clever data structure. Rather than try to sort of cram our data into an array of some fixed size, why don't we keep things simple? Let's take a hash function, for instance, mod 6, which is the size of the array, and let's just say, you know what, if number 7 wants to go here, well, let's let him go there. So again, if number 7 wants to go here, because 7 mod 6 gives me 1, well, that's fine. Let him go there. But what data structure can we borrow from last week to sort of make this happen and keep everyone happy? Well, why don't we just sort of chain him together? So just link this guy here. So our hash function is still very straightforward, and we don't create this sort of arbitrary mess of just giving up and finding the last available location to plop number 7. Put him where he wants to go, but maintain a separate linked list. And so if you have now n elements that you're inserting into this thing, but your array is of size m, in this case 6, what you can do, if you sort of assume that you're inserting a whole lot of data into this array, you're going to get collisions. But that's OK, because these chains just grow laterally. And if your hash function is pretty smart, every one of your chains is going to be roughly the same length. And so what you kind of get is now big O of n over m, where m is the number of elements in your array, which certainly for large enough m does chip away in the real world at what your running time is, even though asymptotically it's still linear. So when it comes time to implement the fastest spell checker possible, students have found that a linked list, may be slow but straightforward, since we've given you a lot of the code, is absolutely an approach you can take. You can absolutely take the approach of a hash table, which actually tends to be among the fastest, and you can even get so fancy as to create a tree, not out of linked lists, but out of arrays. So every node in your tree, as we'll call it on Wednesday, is an array, and you can have what's called a trie. So more on that and in those improvements on Wednesday.